Solar flares are exploding right now, lighting up skies with auroras, knocking out satellites, and making global headlines. The sun isn't just our life giver, it's a raging nuclear powerhouse with the power to create and to destroy. This is Anantum and beyond, and today we're unleashing 100 incredible facts about the sun, from the storms blasting Earth at this very moment, to the mysteries buried deep in its core, and the fiery fate that awaits our star. Let's dive straight in. Solar storms and flares. Solar flares are giant explosions on the sun's surface, releasing energy equal to billions of nuclear bombs in just minutes. They're classified by strength. B and C are minor, M-class can disrupt radio signals, and X-class flares are the most powerful, capable of impacting Earth globally. The largest solar flare ever recorded struck in October 2003. Labeled X45, it was so intense it overwhelmed instruments designed to measure it. Most solar flares erupt from active regions around sunspots, where magnetic fields are twisted and unstable. When aimed at Earth, strong flares can cause radio blackouts, disrupt GPS navigation, and even affect airplanes flying near the poles. Solar storms also pose a risk to satellites, damaging electronics and shortening their lifespan. In 1859, the Carrington event produced auroras as far south as the Caribbean and caused telegraph wires to spark, one of the strongest storms in recorded history. Solar storms are responsible for the dazzling auroras we see, as charged particles collide with Earth's magnetic field and upper atmosphere. The number of flares follows the solar cycle. During solar maximum, when sunspots peak every 11 years, flares and storms become far more frequent. Today, satellites like SOHO and the Solar Dynamics Observatory give us hours of warning before solar storms reach Earth. Vital protection for modern technology. Sun's layers and structure. At the sun's core, temperatures reach 15 million degrees Celsius, hot enough for nuclear fusion that power the star. Photons born in the core bounce around in the radiative zone for up to 100,000 years before reaching the surface. Above that lies the convection zone, where plasma rises and falls in giant cells, carrying heat outward like boiling water. The photosphere is the surface we see, glowing at around 5,500 degrees Celsius, with granules just 1,000 kilometers across. During a solar eclipse, the reddish chromosphere becomes visible, forming a thin glowing layer above the photosphere. Beyond it lies the corona, a vast outer atmosphere that stretches millions of kilometers into space. Strangely, the corona is hotter than the surface, reaching over 1,000,000 degrees, a mystery scientists are still working to solve. Sunspots appear dark because they're cooler, at around 4,000 degrees Celsius, compared to the brighter surface around them. The photosphere is covered in granules, convection cells that bubble up, each one the size of Texas. Coronal holes are regions where the corona is darker and cooler, and where the solar wind escapes into space at its fastest speeds. Magnetism and sunspots. The sun is a giant ball of plasma, and as it spins, moving charges generate a powerful global magnetic field. Roughly every 11 years, that magnetic field flips completely, with the north and south poles trading places. The full magnetic cycle lasts 22 years, 2 sunspot cycles back to back. Sunspots aren't random. They appear in predictable bands that migrate toward the equator, forming the famous butterfly diagram. Hale's law explains the polarity of sunspot pairs. In one hemisphere, the leading spot is north, in the other it's south, and this reverses every cycle. Solar flares and coronal mass ejections are triggered by magnetic reconnection, when stressed field lines snap and release energy. Coronal loops, those glowing arcs you see in extreme ultraviolet images, are plasma trapped in twisted magnetic fields. Solar filaments are cooler plasma, suspended by magnetism above the surface, appearing as dark streaks until they erupt. Some prominences, massive arcs of plasma, can stretch hundreds of thousands of kilometers into space and last for weeks. Clusters of sunspots and strong magnetic fields form active regions where the sun's most violent storms are born. Solar wind and heliosphere. The sun constantly streams charged particles into space, creating what we call the solar wind. That wind inflates a vast protective bubble around the solar system known as the heliosphere. Voyager 1 crossed the boundary of the heliosphere, the heliopause, in 2012, becoming the first spacecraft in interstellar space. Voyager 2 followed in 2018, confirming that boundary from a different direction. The solar wind is what gives comets their tails, blowing dust and gas directly away from the sun. Fast solar wind streams, traveling up to 800 kilometers per second, flow out of dark regions of the corona called coronal holes. The Parker spiral describes how the solar wind curves into a spiral shape as the sun rotates, carrying magnetic fields with it. When bursts of solar wind slam into Earth, they create geomagnetic storms that can interfere with satellites and power grids. The termination shock is the point where solar wind slows dramatically as it collides with interstellar material. The heliosphere is more than just a bubble. It shields Earth and the planets from much of the galaxy's deadly cosmic radiation. Light and fusion. Every second, the sun fuses about 600 million tons of hydrogen into helium, releasing immense amounts of energy. That energy comes from Einstein's famous equation, E equals mc squared, where a tiny bit of mass is converted into light and heat. In the process, the sun loses about 4 million tons of mass every single second, energy carried away as radiation. Photons created in the core take up to 100,000 years to scatter their way to the surface. Once free, sunlight races to Earth in just 8 minutes and 20 seconds, our most direct link to the sun. The sun constantly produces trillions of neutrinos that stream through Earth and through you every second without stopping. For decades, scientists were puzzled because we detected only a fraction of expected neutrinos. The solar neutrino problem was solved when neutrinos were found to change flavor en route. Fusion in the sun is mainly the proton-proton chain, where hydrogen nuclei fuse step by step to form helium. Though we see the sun in visible light, it also emits infrared, ultraviolet, and X-rays, each revealing different layers of activity. The sun's total power output, or luminosity, is about 3.8 times 10 squared to the power of 6 watts, enough to run our civilization for millions of years in a single second. Sun and Earth. The sun is the engine that drives Earth's climate, weather, and even the water cycle. Seasons happen not because of Earth's distance to the sun, but because our planet is tilted 23.5 degrees on its axis. Long-term cycles in solar activity may subtly influence Earth's climate, such as the Maunder minimum linked to the Little Ice Age. Solar storms can damage power grids, as seen in 1989 when a geomagnetic storm blacked out Quebec. Auroras are strongest at the poles, but during major storms they can be seen as far south as the tropics. The ozone layer shields us from harmful ultraviolet radiation emitted by the sun. If the sun suddenly disappeared, Earth would freeze within days, plunging toward absolute zero in weeks. Total solar eclipses occur when the moon perfectly blocks the sun's disk, revealing the hidden corona. Eclipses once terrified ancient cultures, but now they give scientists vital opportunities to study the sun's atmosphere. The sun accounts for 99.8% of the solar system's total mass, dominating everything else combined. History and observation. For ancient Egyptians, the sun was personified as the god Ra, ruler of the sky and giver of life. Galileo Galilei was one of the first to study sunspots with a telescope in the early 1600s, proving the sun was not perfect. Chinese astronomers recorded sunspots over 1,000 years ago, using the naked eye during hazy skies or with simple filters. The understanding that stars, including the sun, shine from nuclear fusion was not discovered until the 20th century. The first dedicated solar observatories were launched into space in the 1960s, freeing scientists from Earth's atmosphere. SOHO, launched in 1995, has become one of the most productive solar missions, still operating today after nearly 30 years. NASA's Solar Dynamics Observatory, or SDO, provides daily high-resolution movies of the sun in multiple wavelengths. Japan's Hinoto mission, launched in 2006, has provided critical insights into the sun's magnetic activity. The Daniel K. Inouye Solar Telescope in Hawaii gives us the sharpest images of granules and sunspots ever seen. Helioseismology, the study of sound waves inside the sun, lets scientists probe its hidden layers, like ultrasound reveals organs. Space missions to the sun. NASA's Parker Solar Probe is humanity's closest mission to the sun, designed to fly through the corona itself. It launched in 2018 and uses repeated Venus flybys to shrink its orbit closer and closer to the sun. By 2025, Parker has already approached within 7 million kilometers of the sun's surface, a record distance. It carries instruments to measure plasma, magnetic fields, and energetic particles directly in the corona. ESA's Solar Orbiter, launched in 2020, complements Parker by providing detailed imaging of the sun's poles. Ulysses, launched in 1990, was the first spacecraft to travel over the sun's polar regions, providing a unique perspective. NASA's Genesis mission collected samples of solar wind and returned them to Earth in 2004, giving us direct material from the sun. The TRACE spacecraft, launched in 1998, gave some of the best early views of solar loops and flares in ultraviolet. Even Skylab, the first U.S. space station, carried instruments that studied the sun's ultraviolet emissions in the 1970s. Future missions aim to build 3D maps of the sun's atmosphere and magnetic field, helping us forecast space weather with greater accuracy. The sun's future. The sun is about 4.6 billion years old, roughly halfway through its main sequence life. It has enough hydrogen fuel left to shine steadily for another 5 billion years. When the hydrogen runs out, the sun will swell into a red giant, many times its current size. In that phase, Mercury and Venus will be swallowed, and Earth may either be engulfed or scorched beyond recognition. The sun's expansion will boil Earth's oceans long before it reaches our planet, making life impossible. Eventually, the sun will shed its outer layers into space, forming a colorful planetary nebula. What remains will be the core, compressed into a white dwarf about the size of Earth. That white dwarf will slowly cool and fade over trillions of years, becoming a black. That smoothie back on the table is a new late-day light. A smoothie stage day must fall altogether. It can literally shift on the end and lose any kind of way. If you look at the distance mostly for work, totally comes back on that. And that's the first meeting to remember. The sun is too small to ever explode as a supernova. That fate is reserved for stars at least 8 times more massive. Its gentle death will reshape the solar system, with planets drifting away as the sun loses mass. Weird and fun facts. The sun contains 99.8% of all the mass in the solar system, dwarfing everything else combined. It's about 109 times wider than Earth. You could line up over 100 Earths across its diameter. You could fit about 1.3 million Earths inside the sun's volume. Despite looking yellow from Earth, sunlight is actually pure white. Our atmosphere scatters it to appear golden. If the sun were hollow, it could hold 1 million Earths with room to spare. The surface temperature is about 5,500 degrees Celsius, but the core burns at 15 million. The sun doesn't rotate like a solid body. Its equator spins faster than its poles, a phenomenon called differential rotation. Every second, the sun produces more energy than all humans have ever consumed in history. Without the sun's heat, Earth would drop to negative 270 degrees Celsius in less than a month, close to absolute zero. The sun is an ordinary G2V yellow dwarf star, but to us, it is everything, the single star that makes life possible. And there you have it, 100 incredible facts about the sun, our star, our life source, and one of the greatest mysteries in the universe. From solar storms that can knock out our technology, to the quiet nuclear reactions keeping us alive, to the sun's ultimate fate as a fading white dwarf, every fact brings us closer to understanding our place in the cosmos. This is Anantum and Beyond, and you've been watching 50 to Know 100 Facts about the Sun. If you enjoyed this episode, don't forget to like, share, and subscribe. Thanks for joining me under the light of our star. And I'll see you next time as we continue exploring the universe, one discovery at a time.